A very good morning to all of you. Discussing further, as earlier I said, we completed till here in last lecture, if you remember. Uh, we were looking upon this ramp and the step signal. We discussed this ramp signal, this isolated point, and this line and all. And we were on the step signal. If we look at the step signal, it is changing from 0 to a particular brightest value. And we can say that first order has this strong effect to this gray level step signal. So if it is first order derivative, it has the strong effect, whereas the second order derivative have double response. Why it is double response? We get positive number, we get a positive number and then a negative number for a step. If we take the second derivative of a step signal, I get a positive and a negative and then a negative. So we get a double response corresponding to that. So from here we can say from the ramp signal to ramp signal, first derivative and second derivative, we come to know that first order derivative produces thick edges. First order, consider this whole as one edge and this is as pure thick edge, and second order derivative will consider only this part of this part of only this part as edges, talking about like if we are talking about the signals, so final edges, therefore we deduct these edges, है ना, we deduct these edges, therefore we concentrate more on second order derivative. So here more of was discussed in last lecture, so you can just join this to that lecture. Moving forward, what we have is we will see how can we utilize second order derivative in sharpening of the image, or we can say in image enhancement. So for the image enhancement, what do we require? We require isotropic filters. And what do we mean by these isotropic filters? Isotropic filters are those filters which do not depend upon the direction of discontinuities. Which means which means that if we are rotating the image in any direction, just hear to me carefully that if you're rotating the image in any direction with any angle, then to the output of the filter should be same. It should not change from the resolution of image in a particular direction. So this is called as isotropic filter. So here we understand the working of an isotropic filters. Now we will see how do we develop an isotropic filter. So the simplest derivative of isotropic filter is Laplacian operator. I hope you all must have heard about Laplacian operator. It is given by del square f equals to delta square f upon my del square del x square plus del square f upon my del f square. This f here represents an image which is a 2D signal. When we take the partial derivative of f with respect to x and second partial differentiation of f with respect to y, and when we add these two, we call this as a Laplacian operator. Now from the second order derivative, if you remember, I hope you all remember that in second order derivative we have the next instance. Yeah, let me clear you. What you had is this was the next instance, this was the previous instance, and we were subtracting twice of this from the current instance. So similarly, what we are doing here is del square f upon my del square x square equals to fx plus 1 y plus fx minus 1 y minus 2 fx y. What is this fx plus 1 y comma y here? It is the next instance. Fx minus y comma y is the previous instance, and the twice of this fxy is the current instance. Similarly, we can write it, you can see it for the y part, y derivative, del square f upon by del square y square equals to fx comma y plus 1 plus fxy minus 1 minus twice of fxy. What does this mean? This means we are talking about the present instance. This is the next instance, this is the previous instance, and this is the present instance. Similarly, as we have discussed for the second order derivative. Now, if I want to write Laplacian operator del square f equals to, we are writing summation of above two formulas, of above these two formulas. We are just writing, we are just adding them and writing the and extracting the final Laplacian operator. So it is given as del square f equals to f of x plus 1 comma y plus fx minus y fx minus 1 comma y plus fxy fx comma y plus 1 plus fx comma y minus 1 minus 4 times of fxy. See, both these twice of current instances will be added, and it will become 4 times of that current instance. So this is the result of Laplacian operator applied on an image. Now, if I want to declare the filter coefficients from this equations, this is similar to the way we applied previously. We multiply the filter coefficients by the coinciding pixels. And we know that fxy is the pixel intensity which is coinciding with the center pixel. So minus 4 would be the weight of center pixels of the filter or the mask. I hope you understand. What we are saying is we are just applying it, and we will get minus 4 as the weight of the center pixel of the filter or the mask. So moving further, we can see minus 4, here you can see, would be the coefficient of center element of filter. And if we say the first part of Laplacian operator of center is fxy, this is fxy. And then we have x plus 1, x plus 1, x plus 1 y would be x plus 1 y, next row, and y would be same, that is this row. And similarly, you can see the other coefficients also. These 4 values, where you can see the 1, this is the center coefficient, and these 4 values actually represents the orthogonal elements of the filter. So orthogonal elements is 1, and diagonal elements, you can see it, see diagonal elements are 0. So this is how we can get mask or a filter from this equation. So now if I apply this mask on an image, this is your fxy, this is your fxy, this is your fxy plus 1, see, and this is your fxy minus 1, this is your, this is your fx minus 1 y, and this is your fx minus 1 comma y. So they all will be multiplied and added together. So we will get this expression. So this is how we apply Laplacian operator on an image. And then we know that filter is slided all over the image pixels in x direction and y direction. Now this pixel is isotropic with incremental angle of 90 degree. What does this means? This means if I rotate the image by 90 degree, the result will be still the same, because orthogonal pixels have some same values, and even if I rotate it with 90 degree, it will get the same filter again. So if it has an isotropic nature with the increment angle 90 degree, now if I consider the diagonal pixels too, so here you can see along with the with their 4 orthogonal pixels, I have added the diagonal pixels too. So when I am adding diagonal pixels, I have to subtract these current pixels 4 times more. So I get the center pixel coefficients as minus 8, and remaining these pixels or coefficients will be 1. So this is the Laplacian filter with 45-degree incremental angle. Now these mask or these filters can be implemented by using this method. Using center pixels, center coefficient is positive and remaining coefficients are negative. And previously you have see or you have seen that center pixel was negative and remaining were positive. In this last one also we observe the same. So this is how we can implement Laplacian operator on using filters on images. Hope this is clear to you. Now moving ahead. Now how do we enhance images using Laplacian filter? If I add what actually we get out of Laplacian filter, so Laplacian filter is our second order derivative. It gives us fine edges or fine information. It produces us so when we get the finer information and it is added with the original image, then actually we get the enhanced image. Now in the figure we can see we have you can see this. This is the first image and this is after applying the Laplacian operator. So with the formula, you can see that it gives gxy equals to fxy minus del square fxy, or and the other one is fxy plus del square fxy, fx comma y. If the center coefficient is negative, we use this formula. And if the center coefficient is positive, we are using this one. The another one, okay? Uh, the image would be enhanced image. After applying this, the image would be an enhanced image. Now let's see how the Laplacian filter is applied to the images. This image is the image of a north pole of moon. Now if the second order Laplacian filter is applied on this image, we get this kind of image. You can just see. So you just see the edges. Here you can see that the edges are clearly visible. But since here we have a step response from dark to bright, so it is a step response. So we have got double response here in this output. It's visible. Now if I want to see this image more prominent, we will scale the image. Scaling means a constant value of gray level is added to all the pixel intensities. After this scaling, this image will look like this image. After this scaling, this image will look like this image, and this image is enhanced using Laplacian. In this, we add these two images, we get this enhanced image. Now you can clearly see that here the details are clearly visible. Edges are properly visible, and you can identify the regions very properly which are not clearly visible in the original image. So this is how we can use Laplacian filter in the image enhancement. So moving further, now if I have filter coefficients which will directly enhance my image. So for image enhancement, what we do is we add Laplacian filter output into the original image. Okay. What we are doing is we are adding the Laplacian filter output into the original image. If center pixel is negative, that is if it is -4, in that case we subtract it from the original image. So -4 will become +4. And these four coefficients will be negative. So this f4, fxy and fxy total makes it 5 fxy. See, this 4 fxy and this fxy, it makes it 5 fxy. And minus all these coefficients. Now if I want to write filter coefficient corresponding to this equation, then you see that fxy is the coefficient. The multiplier of fxy is coincided as center coefficient. So this is the center coefficient and this fx plus 1 comma y is -1. So all the orthogonal coefficients you can see are -1 and center coefficient is 5 and other diagonal coefficients are 0. This will This filter will directly enhance the image. It is not the Laplacian filter, it is the filter which will enhance the image, and this filter is also called as composite mask or composite Laplacian mask. So here this formula is given by gxy equals to fxy minus fx plus 1 comma y plus fx minus 1 comma y plus fx comma y plus 1 plus fx comma y minus 1 plus 4fxy equals to, see, we are adding this and it will give you 5fxy and minus fx plus 1 comma y plus fx minus 1 comma y plus fx comma y plus 1 and plus fx comma y fx comma y minus 1. So applying this formula, what you are getting is you are getting an enhanced image, and this filter is also called as composite mask or composite Laplacian mask. This is your original image, you can see here. This is your enhanced image using composite mask. And this is the enhanced image using composite mask which does not include diagonal elements. And in this image you can see the lines. See, if you just, these lines, if you can just observe these lines in the original image and these lines in the original image, and you can see the same lines here. You will just see the difference. In this, the image you can see the lines are 45 at 45 degree are also enhanced in the output image. They are really sharpened and they are enhanced. They are visible they are prominently visible. So in this way, we can apply the Laplacian operator and enhance our images more properly. So this was all about today's lecture. I wish you all stay home, stay safe. We'll meet soon. Thank you.